Alright, video 3 of 4 for kinematics in 2D. Pretty sure I said last video was tricky. This one, I don't know if it's more tricky or around the same difficulty. I'll leave it up to you. But this is where the fun happens. In kinematics in 2D, this is the main part. The other stuff is just your appetizer. Here's your actual main course, whatever you like. Burgers for me. I don't know what you want. Okay, let's do it. Projectile motion, we got type 1 and 2 today. Next day is going to be type 3. So we are going to revise what perpendicular vectors mean. And we're going to solve some questions. That's basically every set of notes is solving questions. Recall from last lesson. Perpendicular vectors are independent, meaning side to side, are independent of up and down. So imagine we've got this disgusting rat that is being kicked in a nice parabola. If you want an interesting story about that, ask me in class. I've got a not fun rat story. So anyways, we've got X component. This is our side to side. So as this rat is flying through the air, the X component will be independent of the Y component. So X component, sideways, there is no net force, meaning there is nothing pushing this rat sideways when it's flying through the air. Its momentum, or its inertia, is causing it to continue to move. So if there's no net force, acceleration is 0. This just means it's not speeding up as it goes along. So therefore, in the X component, or in the X direction, our Vx is equal to dx over t. That's the only equation. We just need a constant velocity equation. In the Y component, which is up and down, then we have force of gravity. This is causing your rat to fall back to the ground. It goes up, and it has to come back down. So if we have force of gravity, we've got an acceleration of negative 9.8 meters per second squared. The negative means down. We know this already. I taught it last unit. That should be as no surprise. So the Y component, same as last unit. Use the big three equations. Now we're just adding an X component. That's the only different thing that's going on here. And the only value that is going to be the same in X and Y is time, because time is a scalar, so therefore it can go both the same as X and Y. If I have the time for the rat to go up and down, it's going to be the same for it to cross the X distance. Let's do an actual example here. So we've got a student sitting by a window and has a brilliant idea to throw their biology textbook out my window, which is 11 meters high. I did not measure that, I guessed. The textbook is thrown horizontally at 3.2 meters per second. First part, how long is it in the air? What's the time? Here's our situation, biology 11, out the window. We want to first break all of our stuff into X and Y. So this table is very handy for you to draw out when you're starting with projectiles. Split things up, X and Y, so it's very clear. In the X, I have Vx, dx, time. For Y, V initial in the Y, V final in the Y, I've got an acceleration in the Y, dy, time. When you start off and you don't know what to do this, because if you put numbers into here and they're correct, automatic marks. So it's worth doing this if you're stuck. Just automatically, 2 dimensions, make this table. That'll give you 1 mark out of however many. Now let's start filling in what we know. We know that the initial velocity is 3.2. And since it says it's thrown horizontally, that means it's all X component. There's no Y components. Our Y component is actually 0. It's thrown sideways, so nothing up and down. Acceleration, yeah, we're on Earth, so it's negative 9.8. dy is negative 11, because it's going down. Down is negative. So dy equals v naught t plus a half at squared. Here's an equation we can use to be able to solve for time. Since v initial is 0 in the y direction, that just cancels out. And notice here when I wrote this equation, I put some y's in the subscript. This is so you know which variables you're dealing with. Because then you might be tempted, when you said v initial, it should be 0, you might put 3.5. Like half the class ends up doing this because they're not paying attention to that. So be the half that does it right. Plug in numbers, go ahead and solve for time. I'm going to show you the steps here, but essentially you're just doing some algebra. And time is 1.5. That's how long this textbook is in the air. All right, now we want to know how far from the base of the window will the textbook hit the ground. This is our dx. That's the sideways motion. We got the time from last one, so we put that in here for X and Y. Now for x, we just have this simple equation. We have Vx, we have time. Let's solve for distance. Sounds pretty straightforward. The last one here, we want to know the textbook's impact velocity. Impact velocity just means what velocity does it hit the ground. It is not the x component, it is not the y component, and it is not 0 because it hits the ground and comes to a stop. Projectiles are while it's in the air. So impact velocity is what velocity does it hit the ground at, is essentially how you can consider that. That is here, that's our velocity, and it's at some angle. So if I were to draw this out, here is my triangle for this. Our total velocity is going to have an x component and a v final y. So I'm going to do a triangle to be able to solve for this. I have Vx, that one's straightforward. It's from the beginning, it hasn't changed. I need to figure out the final y velocity. So here's our equation. Again, our v initial y is 0. So the final velocity is just acceleration times time. Here's our vfy. Notice it's negative because downwards. Our left and down are always negative, right and up are always positive. Then we have our Vx and the final y. We can just use some Pythagoras here. Solve for the hypotenuse, solve for the angle using tangent because I need both of those. So our impact velocity here is 15.04 meters per second at 78 degrees below horizontal. So horizontal, 78 below. Projectile impact, you're just going to use below horizontal instead of east and west because there's no east and west. So there you go. That is your type 1 projectile. Type 1 meaning it's at some height, launched sideways. Type 2 looks like this. It's on a level ground, launched at an angle. So again, type 1, you're at some height, launched sideways. Type 2, launched at an angle on a flat surface. So in this one, we've got me launching a marble. I've got projectile launchers. They're in the class. They're in the back cupboards. So if the marble has an initial velocity of 1.4 meters per second at 38 degrees, we want to know a few things. First thing, how long is it airborne? And we're going to assume with type 2, it always lands at the same height that it's launched at. That's the whole point of type 2. It lands and launches at the same height. Again, set up this table. Let's start plugging in numbers. We know acceleration. That's it. If we ever have something launched at an angle, the very first thing you want to do is you always want to break up that velocity into components, x and y components. So if my initial velocity here is 1.4, I'm going to split this into x and y with your angle here. That's automatically should be your very first thing you do. Because that v initial, the 1.4, is at an angle. It's not your x, it's not your y, it's the combination of both. So you have to split it into x and y. So that we just use sine and cosine. I will slowly go through. But this algebra you should be able to do here, no problemo. Again, get comfortable with triangles. You're going to use a lot of them in this unit. So there you go. That is your x and y components for your initial velocity. So plug that in. Now we can actually solve for stuff. There's a few tricks with this though. If I want to know how long it's airborne, so the total time, what I'm going to do to make my life easier is look at the top of the diagram here. So this is known as t half. The amount of time it takes me to go from the ground to the peak is the same time to go from the peak to the ground. So if I can figure out this half time, I can just times that by 2 and get the total time. And the reason why I picked the half time, at the top, your final velocity in the y is 0. That's what you need to know with this. Because with that, now I can just use this equation here and quite easily solve for the half time rather than do some quadratics. Unless you want to do quadratics. I'll show that later. So here you go. Here's the total time. We just times what we got by 2. This is the time it takes to go up and down. All right, so we want to know how far forward does the marble fly. This is our dx. Simple. In dealing with the x component, it's really easy. Just need the vx and the time, which we've got already, and there's the horizontal distance. Very straightforward. Now we want the maximum height. So we want the height at the top. That should already be a clue. We're using half time. We're not using the full time, we're using the half time. So This is our dy max, or the maximum height. We are going to use halftime and plug in our final velocity 0, because then I can just plug it into this equation here and solve for dy max. Again, I put all the algebraic steps, but I just don't want to talk it all through. So this is your max height, 0.038 meters, which is 3.8 centimeters. But you can leave it as meters. That is your max height. Like I said, here are a few tricks to remember with type 2. First of all, at max height, so at the very top, your velocity in the y direction is 0. There's still x direction, but the y direction is 0. The time at max height is half the total. The time to reach the top, the same as it reaches the bottom. And the launch velocity is the same as the impact velocity, except the y component is down instead of up. So this is only for type 2 projectiles and if you're on level ground. So in this example, the initial velocity is 1.4 at 38 degrees. My impact velocity is also 1.4 and at 38 degrees, except your y component is down instead of up. We saw this last unit with stuff that's thrown up and down at the same height. Similar thing with type 2 problems, this will also help you. So if you wanted to figure out your v initial in the y direction is negative of the final y velocity. There you go, that is type 1 and 2. Type 3 is coming tomorrow. Alright, here's another one. This one's from Fast 5. You will notice a few of these from the Fast and Furious. They don't really follow physics. Anyways, here is a clip from this one. You might have seen this before, and take a look at what is not correct with this one. Alright, so you guys get the gist of this. It goes on for a little bit. Yeah, so this is going to be really tough for two cars, no matter how powerful they are, to pull a vault at all. Like, vaults are heavy. They're really, really heavy. So even if you've got two Dodge Chargers like this, being able to move, first of all, getting it out of the wall, yeah, not going to happen. Second of all, when you have stuff like when they're turning corners... So let's find a scene where they're turning corners. So stuff like this. Yeah, that's going to really make it difficult for them to straighten that off. There's no way. The momentum of that thing as it moves into the corner, assuming they can actually get it up to speed, they're not going to be able to turn. Like for example, this one, that vault is just going to keep on going straight down that street and pull those cars with them, because the cars are going to weigh less than that vault. Even though you have the tree that kind of helps in this case, that is ridiculous. And then to make things even worse, or to make them better, I guess, I don't know, you've got this part where the vault is going through the bank. That part is just ridiculous. There's no way that the cars would be able to keep pushing this thing or pulling this thing as it's going through the bank. They make it look and seem like, oh, the cars are moving a little bit, but yeah, those cars are going to get pulled a lot harder from that. Let alone the fact that this vault keeps on spinning and spinning and spinning as it goes through different turns. So those cables should be quite wrapped, but look at this. Those are nice straight cables. They happen to perfectly correct themselves, and yeah, I don't know. You really need to turn your physics brain off as you are watching Fast and Furious. So, there you go. That is what is wrong with this one.